Is this okay? I just said I'm going to introduce you in English. Because it's easier for you to understand. Well, it's really a great pleasure to welcome Hiroshi Wada again in the National Museum here in Berlin. I remember you were here last year, and I was in Canada, and I was but you haven't been here before. He is a conservation scientist. He's actually head of the Department of Conservation Science at the National Museum in Tokyo. He is in the National Museum even longer than I am in the Latvian. You joined in 2000, so you're like 26 years now in the National Museum. And all his research is about environmental impact of collections and objects. And you have shown us in the past many interesting projects where we have learned a lot from you on monitors, sensors, humidity, air exchange rates, things like that. But today is going to be about vibration, shock impact, and your research about packing objects in Japan. So we are very happy. Please welcome join me in welcoming Hiroshi Wada for the presentation. Thank you.
Thank you. Thank you so much. Good evening, everyone. This is third time I came here to have a lecture. It's an honor to me to have a lecture such a wonderful venue, and special thanks to Miss Christina for preparing all of me, and a special thanks for Mr. Stefan Simon. Thank you. And today I would like to talk about the shock absorption and vibration response characteristics of packaging materials. So I'm focusing on the packaging materials today. In the field of cultural property, natural cotton is very popular. For example, traditional cotton cushions are often used for packaging. As you can see, these photos shows the packaging for the Haniwa pottery or Haniwa object. This packaging is for the international transportation. Here is a short video of me preparing a cotton cushion. I'm still learning how to do this properly, but I wanted to show you how our test samples are made. Ultimately, these cotton cushions were not used in the experiments. This is because, as you can see, they are handmade, making them highly dependent on the worker's skill and resulting in extremely inconsistent qualities. As you can see in these photos, natural cotton is used for both transportation and long-term storage in museums. These photos shows my museum's archaeological storage room. The problem is that we do not have enough information about these materials. So we need to know what effects do they provide and how can we use them most effectively. To answer these questions, we conducted shock and vibration tests. This is how we test the materials. We place a weight here. Place a weight on the cushioning material and drop it. Sensors measure the impact on the weight and the table. We repeat these different weights and thickness. These are our testing specifications. We use a specific weight to change the load area. Our equipment ensures that every drop is consistent and accurate. Okay. This video shows a drop test using a single layer of natural cotton. And this video shows a test with double layers of cotton. You can see that the material behaves differently when it is thicker. This chart shows one of our results. This dotted line is the impact on the table, and the solid orange line is the impact on the sample. We focus on the peak G. Peak G is a peak acceleration, which is the maximum acceleration during impact. We compared two types of cotton, standard natural cotton on the left and polyester cotton on the right. We also tested two types of polyurethane, yellow one and white one. They have different densities, and we tested them in two different thickness, 30 millimeters and 50 millimeters. Urethane is also very popular packaging material in Japan. You can see the yellow urethane in these photos. This graph shows the results of our shock absorption tests for all 6 materials. The vertical axis represents acceleration, and the horizontal axis represents the weight placed on the material. As the weight changes, the acceleration also changes. For the polyurethane materials, both white and yellow, the data forms a clear quadratic curve. This shows the curve. This indicates there is a sweet spot here, for example here, or an optimal static load where the material provides the best protection. In other words, it means that being either too heavy or too light is ineffective. In contrast, for a single layer of natural cotton or polyester, single layer is a blue line, and double layer is orange line. And polyester, we tested polyester from single layer to the 4th layers. The peak acceleration increases linearly as the weight gets heavier. This suggests that these materials have a limited capacity for heavy loads when used in a single layer. Now let's look at vibration. We used the same weights but a different machine. We tested frequencies from 2 to 500 Hertz. In this video, you can see how the vibration changes. We are applying constant acceleration of 0.3 around here, while continuously varying the frequency. As the frequency increases, you can see the output acceleration on the material rising significantly on the material, rising significantly above the input level. However, after passing a certain frequency, the acceleration begins to decrease. This indicates that the vibration being damped after passing the resonance frequency. As we increase the frequency further, the detected acceleration becomes even lower than the input level, meaning the packaging material is now effectively absorbing the vibration. We tested natural cotton with different thickness and weights. The horizontal axis represents frequency, and the vertical axis represents acceleration. The horizontal axis is a logarithmic scale. Once a certain frequency reached around here, for example, once a certain frequency is reached, the vibration transmissibility becomes extremely high. In other words, these peaks indicate the resonant frequencies. The resonant frequency decreases as the thickness increases. To make the data easier to see, I created these 3D surface plots. In a 3D surface plot, to better visualize the relationship between frequency, weight, and acceleration. These figures represent the exact same data as the previous 3D plot, but presented from a different perspective. So horizontal axis represents frequency, vertical axis represents weight. In this visualization, as the acceleration increases, the color shifts to a brighter tone, even within the same color range. So the brightest areas in this figure represents the acceleration was strongest. In the case of natural cotton, we found that the resonance frequency does not change significantly with vibrations in load weight. It remains concentrated at approximately 10 Hz. Furthermore, we can observe that the resonance frequency remains almost the same, regardless of whether we use a single layer or double layers of natural cotton. Here is a 3D animation to show these results more dynamically. We did the same analysis for polyester using single and double layers. The resonant frequency decreases as the thickness increases. This is a 3D plot for the polyester samples. As the thickness increases, we can observe that the resonance frequency shifts slightly toward the lower frequency side below 10 Hz. You can see that around 10 Hz, you can see the resonance frequency in the single layer, but in the double layer, you can see below the 10 Hz. From this result, the influence of weight is unclear. Here are the results for polyurethane. Here we compare the test results for all 4 types of materials. increases the cost. My point is that if the same amount of packaging material is to be used, it should be used under conditions where that material is most effective. Our goal is determining how to use that thickness effectively to optimize both safety and cost. This graph overlays the vibration transmission results for all tested packaging materials under a load of 60 kilograms per square meter. The differences in vibration response characteristics between materials are clearly visible. So natural cotton here, natural cotton shows the highest vibration absorption efficiency, meaning it dampens energy very effectively. On the other hand, polyurethane, this is polyurethane, shows a very distinct and sharp resonance peak. This means that at certain frequencies, polyurethane can actually amplify vibrations significantly. It is crucial to recognize these specific material behaviors during the packaging design process. However, in practice, it is almost inconceivable that we would rely on a single type of cushioning material for every packaging scenario. In other words, in most cases, we package objects by layering multiple types of different cushioning materials. While not covering every possible variation, I conducted variation tests on several patterns of combined cushioning materials to observe their collective behavior. First, I tested two specific patterns using 30 millimeters thickness of white and yellow polyurethane. One pattern had white on the bottom and yellow on top. And other was reverse. Interestingly, the results were almost identical. Regardless of the stacking order, the resonance occurred at the same frequency and the transmissibility remained the same. For these similar materials, the order did not impact the vibration characteristics. However, when we combined different types of materials, such as polyester and polyurethane, the results changed significantly. When polyester was placed on top of polyurethane, the benefits of the polyurethane base were almost lost. In contrast, when polyurethane was placed on top of polyester, the resonance frequency shifted slightly lower range, and the overall vibration transmissibility decreased. This proves that the order of layers is a critical factor in hybrid packaging design. Ultimately, our research aims to ensure the absolute safety of cultural properties during transit. The greatest challenge remains identifying the resonance frequency of the artifacts themselves. Since we cannot perform vibration tests on original masterpieces, we must rely on high-quality replicas and advanced simulations. Furthermore, we must continue to study the the environmental vibrations of trucks, trains. In the future, we may transport cultural properties by drone. By understanding the relationship between the characteristic of the object, the transport method, and the packaging material, we can protect our objects for the future. So this is the end of my slide. Thank you very much for your attention. Thank you.
Just starting to imagine transport by drone. I have questions to Mr. Hiroshi.
I have a question. Thank you. This was really interesting. How many times can you reuse this packaging before it doesn't work anymore? Or is that unlimited?
Yes. In these tests, I use, of course, I use fresh material. And for example, for the cotton test, I tested the weight put on the cotton for some months, but characteristics of the cotton does not change. But other material, I don't know, because I did not such a test, not yet. Okay. Yeah, that's good question.
Thank you.
Yeah.
Yeah, I understand. But for example, here, if you look at these diagrams, you could say, okay, this is at like 30,
yeah,
and here same. It's like you're already there, right? It's not changing much more in the white urethane, but it's totally different in the yellow.
Totally different.
So if you talk to the craftsmen, to the art handlers who do this in the traditional way, do you also talk with them about your? What do they say? Because they do this, right? They don't measure. They have. You say it's a craftsman. It's a way how they manually make wrapping the packaging. Do you talk sometimes to this?
Yes, sometimes for the special object needed to transport, we are sometimes discussing. But normally, our museums every day transport a lot of objects. So I cannot control all of the transportation of my museum object. So I want to make some regulations for using for these data. And difficult is the for resistant against the shock is very easy. Because it's better to select this weight. It's over. But the difficult is how to control the vibration. How to control the vibration. Because we don't know the resonance frequency, we don't know the natural frequency of the art object. Yeah. If we use the natural cotton, but the natural cotton has a resonance frequency around 10 Hz, but the object, natural frequency of the object is around 10 Hz, it was very dangerous. So the problem is how to get the natural frequency of the object. If the object, natural frequency of object is 100 Hz, it is better to use a polyester or a cotton. But if the natural frequency of the object is 10 Hz, it's better to use the polyester. And another complicated thing is truck bed. Vibration of the truck bed. If the truck bed has truck also has a frequency vibration. The transportation method vibration is, for example, 10 Hz. We use cotton is very dangerous. So I should say that the important information is packaging materials and object itself and the transportation vibration. These three information is very important, very complicated. But
Very complex.
Yeah, but generally speaking, the lower frequency is better than the high frequency.
Yeah.
Yeah. For example, the seismic isolation is same theory. Yeah. The earthquake have a very high frequency, but isolator change the vibration to lower. Yeah.
There's more questions for Mr. Hiroshi Wada? No? From the conclusion point of view? I would love to have this project. You know, there was a project in America called Parking Transit.
Yeah, I heard it. Yeah.
Many years ago. It's actually we try to revive it now.
Yeah.
Because many of the main actors are not anymore active. I talked something like end of the 90s, 30 years ago, 25 years ago. And I think it's really, really interesting. And what I always admire in your research in Tokyo and you and your colleagues is that you really aim at putting conditions and parameters into numbers. You have really discussed this very often, but I think this is a very, very good. It's very difficult. It's very complex, as you say, but you don't give up. You want to put the condition into a number so that you can measure, and then your colleagues in Brazil or in Germany can measure, and then you can take the. And if you get this together, this knowledge what you create with the experience of the traditional craftsmen and the cotton people, in Japan, that's probably the best way to do. So I thank you. Thank you very much, and I really look forward to your next lecture.
I will come here next year.
We're looking forward. Thank you very much.